Yes, doctor.
Okay, so we were talking about the center difference for first derivative, which will involve the point just before and just after. So in this case, we do vi plus 1 minus vi minus 1 over 2 delta t. Now for the Euler's forward difference method, we will use the forward difference scheme, and therefore we will replace dv by dt by vi plus 1 minus vi over ti plus 1 minus ti. And then after rearranging terms, we will take vi plus 1 to one side, function of vi and delta t from the other side. Now, what we will do, we will try to solve this problem for a certain time step, okay? So let us consider the following given. So if they gave us the mass of the person, the drag coefficient, and they gave us delta t, we can use the numerical equation to assess the velocity at certain time points. Okay, so this is called discrete solution. Why? Because when we use this method, we will just be able to assess the value of the velocity at certain points. So we will get a discrete solution for the velocity v. For example, here, if we select delta t equal to 2 seconds, we know that v0 is 0. So this is the boundary condition. It should be given. Now, at t equals to 2 seconds, we can calculate v at 2. So anything between 0 and 2 seconds, we cannot calculate it directly here. We can find it by approximation after. But since we are not able to calculate it, then we can say that this is a discrete solution. It will give us just velocity at certain points. And if you want to compute any other velocity at a point in between, we should use approximation techniques. So here, for example, if you want to get v at 2 seconds, we will use this numerical relation. V at 2 seconds will be v at 0 plus 1. So v1, which is at time step at t equals 2 seconds, it will be equal to v0. So we replace vi will be v0 plus g minus cd over m times v square. So I replace v0 by also here times delta t, and I get the value of velocity at 2 seconds. Now I will repeat this procedure to find the velocity now at t equal 4 seconds. So v2 will be equal to velocity at 4 seconds. So when I replace now in the equation, vi will be v1, which is the velocity I got from the previous step. So now I will replace v1 in place of vi in the equation. So I will place it here and I will place it here times delta t. Nothing is changing in the equation, just vi is changing because delta t is remaining the same. Now I get v, this is v2. So now in step 3, v3 will be v at 4 plus delta t, which is 6 seconds. So now to get v3, I just have to replace v2. v2 will be equal to vi in this equation. So I will place it here and here, and everything else will remain fixed. So I can get v at step 3, and I can repeat this procedure until closing my interval. So I am interested here into drawing a velocity variation between 0 and 12 seconds. So if I choose delta t equal to 2 seconds, I will need to do calculation at 6 points. At t equal 2, at t equal 4, t equals 6, t equals to 8 seconds, and t equals to 10 seconds, and t equals to 12. So I end up with 6 calculations. Now, if I decide to get more points, then I can choose a smaller delta t. So if I say I want to take delta t equals to 1 second, let's say, then I will perform, since delta t was divided by 2, the number of calculation will be multiplied by 2. So I should perform now 12 calculations from 1 to 12. And if I take, let's say, delta t equal to 0.5, then I need 24 calculations. So as you can see, smaller is your delta t, you can expect a better accuracy, but also a higher time of calculations. Okay? So always we should try to do a compromise between the computational time and the accuracy of the solution. So now let us see, let us compare the discrete solution with the continuous solution. When we talk about continuous solution, it is the exact solution. So here, as we have seen when we introduced the equation and the differential equation, we said that we have an exact solution. So the exact solution is a continuous solution because we are able to predict the solution at any point we want, at any time we want, by just replacing t in the formula.